All right, we got about a minute to go, so if you guys have any questions, go ahead and ask before class. And good morning and hello. This is we made it to the last day of the first week. We have about 7 more weeks to go. Cool. Yep, we are still on the binary addition module. Because we are not quite done with it yet. I mean, we may be about halfway done so far. So we're gonna have some interesting topic today about binary addition, which I think is good because we're close to the end of the first week. So over the weekend, I'm not going to give you guys a whole lot of homework, but I do want you to spend some time to understand the concepts and the material that we have already talked about this week because the schedule is really compact, so it takes a little bit of time to kind of unpack everything over the weekend. So next week we can start on additional topics. All right, so it's 9 o'clock. I am going to get started. So what you're seeing on the screen through screen share is what we talked about yesterday. Um, and the main topic over here is instead of an actual addition to combine the two sources of carries, we can use a OR instead of an arithmetic addition. And let me scroll up just a little bit to show you why. The reason why we can use a OR instead of a real addition is because the carry to the next column can only come from either the X and the Y bits adding or coming from the Q and the K bits adding, but it cannot come from both at the same time. So when we compare the tables of addition versus logical OR, A and B are bits, okay, so they can only be zeros or ones. The only row that makes a difference is the last row, where 1 plus 1 is 2, but 1 or 1 is just 1. But for the other 3 rows, they behave exactly the same way. So as long as the last row cannot be encountered as a case, then we can substitute the addition that was originally here with a logical OR. And then we analyzed the situation and we found out that A, which is the carry of xi, yi, and B, which is the carry of qi, ki, they cannot be ones at the same time. And that has to do with when A is a 1, that means xi, yi is a 1, or I should say when xi and yi is a 1. But that also implies that xi itself is a 1 and yi itself is a 1. So when xi is a 1 and yi is a 1, then we know qi has to be a 0 because qi is defined this way. It is basically the exclusive OR of xi, yi. So when xi and yi are both 1s, then qi is guaranteed a 0. When qi is guaranteed a 0, then B is guaranteed a 0 as well, because the way we compute carry is really just a logical AND. So when one side of the AND is a 0, then the entire AND has to be a 0 already. We don't even have to look at KI in this case. So that's kind of a quick recap. Excuse me. So that's a quick recap of what we talked about yesterday. And the significance of this entire discussion up to this point is we can use logic gates to do everything for binary number addition. So that's great because we can just reuse all the gates that we have already talked about, which can boil all the way down to the NAND 2 gate, which then boils down to 4 transistors. So we know how to implement this in using physical devices. So that's where we left off yesterday. So what we'll do today is to build a few circuits, okay, just to illustrate how this works. And then we'll find out that the circuit that we are building, even though it works, is less than ideal. Okay, so that's what we'll do next. So what I am going to do now is to draw something by hand first, so that we are not doing it in LogicSim yet, okay? And then later on we can capture it in LogicSim. So what we'll do right now is to say, okay, given x and given y, excuse me, we want to generate a result of x plus y and a carry of x plus y. But we know how to do this already, because in the previous page we already have the equations to do it. Okay, so right here we know that c of xi yi is really just a conjunction, and we also know the r, which we also know as qi, is xi and not yi, or not xi and yi. So we kind of know how to do this already, but I just want to look at it from the schematic perspective using logic gates. So this is also important in this class, is when you look at a Boolean expression, you want to be able to convert it in your head at least, or on a piece of paper, into a logic gate diagram, because those two are interchangeable. Okay, so we'll do with the carry first. So these are input pins, they're squares. These are output pins, they're circles. So the carry is the easy one, because we just need an AND gate to do this. And this is what an AND gate looks like. Okay, so we just have to take one input from X, take the other input from Y, and there we have it. We have the carry bit of X plus Y. Now X and Y, in this case, each one is just a single bit. Then we look at R. Okay, R is a little bit more complex if we want to use the AND gate approach. So, but it's not like it's not doable, it just looks kind of complex, because we need two AND gates, and then the output of the two AND gates would be combined using an OR gate, and then the output of the OR gate would go to the result. So it looks a little bit like this. Okay, so now the question is, what do we feed into the AND gate? Well, we need to negate x first and then feed y that is not negated to the first one. Well, I mean, it's symmetric, so either way is okay. But we cannot just give x and y to both of these AND gates. One of the x and the y, or the y, has to be negated. So in terms of notation, LogicSim supports this little bubble here. So what this bubble is doing is it is negating just that one input pin. So that means if I want xi to be negated to the first one, but not negated to the second one, this is what I can do. So with y, I want it to be non-negated to the first one, to the top AND gate, and I want it to be negated to the second AND gate. So this is going to look a little bit ugly because I did not plan ahead of time like that. So this will basically compute the result of adding x and y as single bits, and also the carry of adding x and y. So do we have any questions about this diagram first? Okay, no questions. All right. And I have to double check to make sure that Discord is still working, because remember, yesterday Discord stopped working. Okay, we got some questions coming. Nice. Okay, go ahead. All right, so Richard asked first, the OR gate is in the middle. So this is the OR gate. This is an OR gate. These are AND gates. There we go. And then Bopinda has a different question. Can we put the bubble on the front of the gate? Yes, but that means we're negating the output and not negating the input. So yes, we can, but it's not equivalent to what we are doing here. So you can also see how the bubble means negation, because in the case of the P and N transistors, remember that the P1 has a bubble because when the input or when the gate is low, it turns the gate on, or it makes the gate connect. So that's, well, not the gate, but the transistor connect, and that's why there's a bubble for the P-type transistor. Okay, So when we look at this, we go like, okay, that works. But we can do the same thing, okay? So instead of x, we can call this q. Instead of y, we can call this k from the previous column. And we can now also generate, instead of r, we have the sum bit. And the carry is kind of the awkward one because it has to go to the next, column. So we're going to put a question mark here. But we can see how this design can be reused, okay? In other words, what we are looking at here, okay, let me put a box around the whole thing. So if I make this into a subcircuit, okay, so this is just what I want to identify as a subcircuit, okay, it can now be used to perform 1/2 of each column. Okay, so if I scroll up, okay, well, this is not in base 2, but it serves the same purpose, okay, because when we have xi, yi, and we want to compute the q, and it contributes partially to this carry, and then we want to add q and k to come up with the sum, but that also partially contributes to this carry. So the first half, okay, let me use a different use a highlighter to indicate which half we're talking about. So this is 1/2 of adding of one column. This is the other half of the column. Now, are the two halves related? Well, they're obviously related because q or rxy depends on xy, and then k depends on the previous column if there's one. But both of these will contribute to the carry of the next column. So we want to somehow capture that information when we use a subcircuit that looks like this. Okay, so now we want to do some work in LogicSim because I want to make this circuit functional. We can actually so that we can actually play with it. So let's go to a LogicSim window. I don't think I have one open. Oh, I do. I just passed it. Just went right past it. All right, so there we go. All right, let me put it back here. All right, so we're going to start a new file because we are now talking about addition. So I'm starting on the new file, and here's our new file. So we want to capture what we call, what we will call a half adder. And just like before, we're going to have the XY input pins. And the output pins. Now I'm going to label these a little bit later. And then we'll go ahead and draw the circuit in between. So we go to gates. We go to AND. And you can see how the default AND gate is a little bit big and it has 5 inputs. So you can also see from the property table that it has got 5 inputs. We only need 2. It is very important that you do not have more input pins than you need, because if you have additional input pins and they're not connected to anything, in LogicSim it seems to work okay, but in reality, if you have an input pin to a device that is not actually connected to anything, it's called floating. And any signal that is floating is basically, it has an undetermined value, which also means, when you actually run that circuit in real life, the value presented to that pin will depend on kind of a lot of things. Like if you turn on the microwave next to your device, it might start to flip between zeros and ones. If you touch it, it might it might just be determined to a 1 or a 0. So we don't want that sort of things to happen in a real life circuit. So it's really important not to leave input pins unconnected. All right, so there we go. We got an AND gate here. Yeah, we can lower this a little bit because we're gonna have some additional stuff that we need about that. So we are now almost done with the computation of the carry. There we go. Okay, so this is the carry output. These are the 2 bits that we are adding. So now we want to look at the other one, which is the result. That one, I could have just used exclusive OR, okay, the XOR gate, and just put 1 over here and be done with it, okay. But I still want to kind of show you guys how to do it in case you do not have access to a exclusive OR gate. So what we'll do is we are just going to be duplicating these gates a few times, twice to be exact, like so. And with the top one, I'll just make everything resemble exactly what we did in the hand written version. So you can also see, I have just selected the AND gate, and you can see in the property table of an AND gate, it allows you to specify, individually which input do you want to negate. So right now, neither is negated, and that's why we don't see any bubbles here. So if I want to negate just the top one, I can just say yes to the top one, and if I want to negate just the bottom one, I can just say yes to the bottom one. So the question is, can we negate both of them? The answer is yes. Okay, if you have an application where you need to negate both of the inputs, you can do that. But we cannot negate the output, because when we negate the output, it becomes a NAND gate. So you have to choose a different gate if you want to negate the output of the AND gate. All right, so we are almost done. Okay, so we just need to hook up a few more wires, like so, and this one goes all the way here. So now we have, oh, okay, I forgot one thing, didn't I? Because I need an OR gate to combine the output of the 2 AND gates. So I go pick up an OR gate, and it's going to look too big. Now, if for this class, we are not going to use 5 input OR gates too much, this is something you can do, is to go to OR gate, but before you put an instance of that OR gate over here, you go to the property table, and then you change the number of inputs to the usual number that you want, which is 2, and then you change the gate size to narrow. So now what we have done is we are changing the quote-unquote class definition. So every time we make an instance out of this class, it is now changed. The default has changed basically. So it's a really kind of useful feature, because if all we really want in this class are mostly, not always, but mostly 2 input gates, you can just go ahead and change the default. So this way you don't have to keep changing it after you make an instance of a gate. All right, so now we got it. Okay, so now we got this circuit. It has got 2 inputs and 2 output pins. The 2 input pins are kind of interchangeable because addition is commutative, but the output pins, one is the result, and then the other one is the carry of adding those 2 input pins. So let's go ahead and play with this a little bit and see if it makes sense. Okay, there are only 4 possible input patterns to this, because these 2 input pins are independent, which means we're looking at a truth table that has potentially 4 rows. So let's go ahead and play with this. 0 plus 0 has a result of 0 and a carry of 0. Okay, seems to work. 1 plus 0 has a result of 1, but it also has a carry of 0. 0 plus 1 has a result of 1 and has a carry of 0. And then 1 plus 1 has a result of 0, but it has a carry of 1. So I have just tested this circuit and pretty much exhaustively, because these are the only possible combinations for this particular device. So now I can turn this into a subcircuit, and to turn something into a subcircuit after the fact is pretty easy. You just go to the circuit appearance, and I probably want to label it, okay, because the 2 inputs are not the issue, the 2 outputs is the issue. Because if I don't label it, I cannot remember which one is which one. So I want to clearly indicate which one is the result and which one is the carry. And then I can fine-tune the locations of the caption. The squares and also the circles, they disappear when we use this as a subcircuit inside another circuit. So you can basically put things or text caption that is really close or even overlapping with the circle or the square. It doesn't appear in a larger circuit. So now we have this subcircuit, and it's probably a good idea to rename it too, because this is really not my main circuit anymore. This is a subcircuit that I'll be using inside other circuits. So instead of calling this main, I'll call this half-adder, because that's basically what it is. It is half of an adder. It handles 1/2 of the column when we perform addition. Okay, so let me just kind of pause here and see if there are any questions. It handles actually both the top half and the bottom half of the circuit. So let me just go back to Zerno, and this time we're going to look at a base 2 addition, multi-digit base 2 addition, just so that after that we can come back to this circuit and then continue to build the larger circuit. Can we resize the circuit? I'm not sure what you mean by resizing. Do you mean zooming in, or? Yes, okay. So the zoom control is right here. So you can zoom in and you can zoom out. Okay. All right. So hold on a second. I have to take off my mic because I got something in my eyes and I need to take care of it first. Okay. Hopefully it's better. All right. So let's switch back to Zerno. That right here. And what we'll do is now we'll look into a base 2 addition, multi-column base 2 addition. So let's just say that this is x. Let's say x is 1, 0, 1, 1, and this is y over here. And let's say y is 0, 1, 0, 1. This is an addition. Okay. So remember, we got the 3 additional rows. Okay, this is the Q, this is the K, and this is the sum. So right away we can see the 2 additions, right? Because per column we have x plus y. X plus y will give us 2 results. The r goes in this place, and then the carry contributes to this space over here. So now we say, okay, 1 plus 1, has a r or a result of 0, and it has a carry of 1. So I can put a 1 right away to the next column, because if 1/2 addition is giving you a carry, then the next column is going to have that carry. There's no question about it. Then we have to look at Q plus K. This K is by default 0, so we have 0 plus 0, which is 0. But do you see how, well, even when you look at the equations, you already know that Qi is the result of adding xi and yi. And then the sum of bit I is the result of adding qi and ki. This is actually in yesterday's slide, so it should not be new to us. So now the question is, what about this guy over here? Well, that's ki plus 1. And we also know what that looks like, because it is the carry of xi plus yi. And let me be very specific here and use a OR, logical or the carry of qi plus ki. All right. So now moving on to the next column, 1 plus 0 has a result of 1. It has a carry of 0, so I cannot quite determine whether to put a 0 or 1 over here. Then we have the 1 plus 1, which has a result of 0. But this 1 plus 1, which is q1 plus k1, has a carry of 1. That carry goes here. Now we move on to the third column, or column 2. This is column 0, column 1, column 2. 0 plus 1, once again, has a result of 1. Itself does not contribute a 1 to the next column, so I cannot determine yet at this point. But then when we look at 1 plus 1, it has a result of 0, but it also has a carry of 1. So now we put a 1 over here. And you can see that it's going to be about the same over here. 1 plus 0 is a 1, has no it has a carry of 0 on its own. 1 plus 1, on the other hand, has a 0, but it has a carry of 1. So that is the actual result of this particular addition. Do we have any questions about this example? All right, so looks like there are no questions about this. And once again, I'm just going to double check and make sure that Discord is still working, because sometimes when I don't get any questions, it's not because there are no questions, it's because Discord itself has crashed. Okay, somebody is typing. Okay, so Jargon is asking, so now we have to build something that will take care of ki plus 1. Yes, so ki plus 1 is not taken care of by the half-adder. What about the extra 1 to carry? You mean the overall carry, this guy over here? That one is not stored as a part of the sum, but it will still be the part of the output of this 4x4 adder. All right. So once again, let me double check. Yep, Discord is still working. All right, cool. All right. So as I said, the last carry bit is kind of part of the output, but it's not part of the sum of the addition. It is just the overall carry of the addition. Cool. So what we're going to do now is I'm going to label the two half-adders of column 0. The first half-adder needs to handle this portion. Okay, that's our first half-adder. And then the second half-adder has to handle this portion over here. Now, when we are dealing with these half-adders, the first half-adder, one part of the output, is the result, which goes into here. When we look at the second half-adder, part of its output is the result, and it goes into the sum like that. But in terms of the carry bit, both of them go to the one of the next column. So in other words, the carry of x0 plus y0 partially contributes to this one, but the carry of q0 plus k0 also partially contributes to this carry over here. So we have to combine those two using an OR gate. Okay, the reason why we know that we need the OR gate to do this is because of this OR over here. So do you see how this OR here? That shows us how to do it. If I want to use the correct kind of highlighting, so this is in orange and this is in purple. Don't see my OR. It's not in the diagram yet, but it is in the equation. So the OR, which is what we need to do to apply to this portion here to combine the two outputs of x plus y as well as q plus k, is this OR over here, which does not have a gate yet in the design that we have. All right, cool. All right, so now we know how this looks like. Now we go back to our Logisim circuit, and we'll try to build a full adder this time. So what a full adder is going to do is it's going to take care of an entire column. So it will take X, Y, and then it will do everything for the entire column. It's going to have one output, to the next, to the carry of the next column, and it's going to give us one sum, which is this portion over here. Okay, so that's what a full adder is going to look like. But we will also kind of make sure that the full adder is going to take the input, which is the carry that's going into this spot over here. So I know it's, this picture is getting really kind of crowded. So let's go ahead and take a look at the Logisim design, because I think that will help clear up the concepts. So let's go back to this Logisim. And now we are done with the half adder. It's time to create a full adder. So we say add circuit, and this time we have a full adder. And when we have a full adder, we already know it's going to need two half adders. So we click half adder and basically slap two of these things into this design. You can make it side by side, you can make it top down. Side by side is slightly better. It's not a whole lot better, but it's just a little bit better. And we also want to define the inputs, which are basically, they're kind of like parameters to a subroutine. So we have X, the original X, and the original Y. We have two outputs. One is the sum. The other one is the carry going to the next column. And I'm forgetting one extra input, which is the carry coming in from the previous column. Okay, so now is a good time to actually, would that be, yeah, I think that would work. So it's time to label these input pins. So I'm going to call this one CIN or carry in, and I'm going to call this one CInOut or carry out. So this has nothing to do with CIN and CIout in C++, okay, because C in this case means carry and not, I don't even know why it's called CIN and CIout in C++. What does the C stand for? Does anyone know? Because I know those are streams, but console. Okay, thank you. Kind of makes sense, right? They should have called it standard in and standard out, basically using exactly the same terminology as in regular C and not change the name to CIN and CIout. But that's just my opinion. All right, and then these two are X and Y. So we have X and we have Y here. And you can also see why you can also see that I do not have an index. In other words, X and Y are not X0, Y0, because regardless of the column, it's going to look exactly the same. Okay. And then this one over here is our sum. Okay. There we go. So I got all the input and output pins labeled, and it's time to draw the actual connections into the half adder. Okay. So X and Y, are going into the first half adder. The result of the first adder goes to one of the inputs of the second half adder. But what about the input, the second input of the second half adder? That's coming in from the carry input. So the carry input goes to the other input of the second half adder. The R output of the second half adder is the finished product for one entire column. That is the sum. And then the second output, which is the carry, is going to be used by the next column, which this circuit cannot show because basically it will be another instance of this circuit. So do we have any questions about this picture? Okay, we got 2 people typing. Okay, Richard first. Where does the first carry from the first half adder go? You mean the input, like Cin? You can tie it to a constant. You can also tie it to something else in the processor. So it depends on the architecture. Some architectures hook it up in a more flexible way. So you can basically use the carry flag from a previous addition as the carry in of the next addition. In some other cases, the least significant bit, for the least significant bit, the carry in is tied to the constant of 0. The output from the first adder, it goes into the input of the second adder. Okay, and then Bullpinder is typing the first half adder. Oh, right. Okay, I messed up here. Because these 2 outputs, the 2 carries, are supposed to go into an OR gate before they become the actual output of this particular full adder. Thank you. Good job. You guys spotted the problem. Okay. So now we go pull a OR gate. And you can see how this time when I pull the OR gate, it is already having only 2 inputs and the size is already smaller. Okay, so we want this to be all the way over here. And then use 1 carry to go to 1 input. And then use the other carry to go to the other input of the OR gate. So I totally messed up initially. There we go. Good job. Okay. So now we got it. Because the output of this is basically C of XI, this is basically C of QI, KI, and this is KI plus 1. This is KI minus 1. So if we want to label everything, relatively speaking, using I, does anyone want me to do that? To use the relative I thing? Maybe. Maybe not. Yes. Okay. So Cin, okay, if I use that terminology, is K of I minus 1. So I'm going to use the underscore to mean subscript and then I minus 1. CInOut is basically the next carry. So that is basically, nope, I take it back. I take it back. This is just Ki. So Ki is correct. This is Ki plus 1. All right, yep, they're all relative. And this is Xi, and this is Yi. The I is an index that tells me which column we are dealing with, and this is Si itself. So everything except for Ki plus 1 are on the same column. So I think this is good because this helps us understand how to look at this picture and relate it back to the example that we have just gone through. All right, so are we okay so far? All right. So now it's time to turn this into a component by looking at the packaging. So if this packaging looks a little bit too packed to you, okay, you can actually go ahead and change it. But for homework assignments or for labs that you have to turn in the Logisim file, I would try to just keep it the way it is because the slightest change of the pin positions is going to mess up the automated grader script because in order to substitute a part with another part, the pin locations have to be exactly the same, and the part has to be named exactly the same as well. So I'm just going to leave these things alone, even though I will label these. So one is CIN, and then we got X, and then we got Y, and then we got the sum bit, and then we got CInOut. Okay, you'll carry out. And then we just need to move these things into the right spots. So CIN can, I'll move it outside of the box. X and Y can go inside the box. The sum bit can go inside the box as well. And then CO probably can, oh, okay, that fits. There we go. So CI is the only one that may not fit, but looks like we can kind of squeeze it in and make it fit. There we go. Okay, looks kind of ugly, but you know, everything fits. So this is now a full adder, which corresponds, let me go back to Logisim here, which corresponds to handling one column. So when we look at Zernal, I said Logisim, but I meant Zernal. So when you look at the blue box is basically a full adder. And inside the full adder, we have two half adders. The first half adder is the orange box, and then the second half adder is the purple box. And then the green thing is what combines the carry output of both of those boxes to become the output of the blue box. And that's also what I forgot initially when I worked on the full adder in Logisim. So do we have any questions basically relating? Let me see if I can do this. Let me see if I can show both at the same time, because this way you can look at the Logisim diagram and also look at the hand-drawn example at the same time. So let's see if we can just do a full adder. And yep, okay. So do we have any questions, basically relating the blue box, the light blue box being the entire circuitry in Logisim, and then the orange box being the first half adder, and then the purple box being the second half adder? So are we good at this point? Okay, we got June. Is it June or Jun? Short U or long U? Okay, Catherine first. The green is the OR gate. Yes. So, there we go. So the green part, which is here, okay, I'm not sure whether you guys can see my pen here. So the green part here is corresponding to the OR gate over here. So Catherine is correct. June, okay, long U. So June is saying, so basically, that basically means if we want to do more row additions, all we need is to use the carry k+1 and wire it to another full adder. That's exactly it. Okay, so this is really kind of cool, because now we have a design that is quote-unquote stackable, right? So let's go ahead and go to the circuit here, and this time we are going to add another circuit, and we'll call this a 3x3 adder. Okay, in other words, it takes 3 bits, it adds 3 bits to another 3 bits. It will give us a sum that is also 3 bits, but it will give us an overall carry in case the sum actually does not have enough bits to store the result. So what we do is we now slap 3 of these things, right? And there are different ways to look at this. I just want to kind of go through the design a little bit to figure out what is the best way to show this. I think this might work. Okay, so we'll see. So this part is really just kind of artistically, which way is the best way to show the dependency between the full adders. So now we need a 3-bit input, okay, which is X, and then another 3-bit input, which is Y. So we'll call this X, and it's a 3-bit input. Now I duplicate it so that I just have to change the label. Instead of X, this is now Y. And as I said a little bit earlier, a lot of designs just hook up a constant of 0 to the carry in of column 0. So I just go to wiring, pick up a constant, and change the value of the constant from 1 to 0. So now we have a constant of 0 to hook up to the carry input of the first one. But some other designs would actually just use a pin instead of a constant, so that way you can toggle it and change it from 0 to 1. In fact, let's do that. Let's turn this into a pin, so we have the flexibility of toggling this from 0 to 1 and then back if we need to. Now X is a 3-bit thing, and this X over here is a 1-bit thing, and so is this one, and so is this one. So this time we need a splitter to kind of split X and Y into the individual bits that we need. And we'll go ahead and play with slightly different options of a 3-end splitter. So we first pick up a splitter first. Okay, so we go pick up a splitter. There we go. And the default is 4 in, 4 fan out of 4, and bit width of 4. And I think that's because I changed it, to do something. Okay, that's the change. That's a changed default. So in this case, we need a 3-bit splitter that has a 3 fan out. And the default is fine, okay, because we do need all 3 bits, each one to go to one particular full adder. So this is fine, and then we'll have a duplicate because Y needs exactly the same thing. And this doesn't look very nice. Okay, so if it doesn't look nice, you can actually do it to both at the same time. Is instead of using a left-handed appearance, I think we can change it to a right-handed appearance, which basically just flips it, up and down this way. But if you look at each one, you can actually change the appearance as well. Nope. Okay. Oh yeah, you can change the appearance. You can change it to be centered like this, or you can change it to legacy, which is like that. Okay, and that's kind of ugly. That looks like a chicken foot to me. So we'll change it back to the right-hand design. So all this stuff here, what I'm playing with right now, is really just kind of, does it look nice? So you can kind of ignore all of that stuff, if you just want it to be functional. So bit 0 of X, which is X0, goes to the first adder. And then Y0 also goes to the first Y, or go to the Y of the first half adder. Bit 1 of X goes to X of the second full adder, and Y is the same way. And then bit 2 goes to the last one. Now in the case of adding, whether you plug in the X to the X or you plug in the X to the Y, doesn't really matter, because as I said a little bit earlier, addition is commutative. But if you're dealing with subtraction, then you cannot flip it, because subtraction is not commutative. So now this is why I stagger the half adder, because the carry output of the full adder for column 0 goes to the input of column 1, and then the output of column 1 goes to the input of column 2. And now we have the sum bit of 0, the sum bit of 1, the sum bit of 2, and the overall carry. which means it's time to duplicate the splitter again so that we can get to the sum. And this time we needed to flip left right, so that's the phasing control, like so. And it's important to observe, which one is bit 0. The top one is bit 0, which is kind of the way I want it. So there we go. We got 1, and then we got 2, and then we got 3. Ooh, this looks nicer than I originally anticipated. I thought this would look really ugly, but it does not. Nice. So this is our sum output, which is also 3-bit wide and has a label of S, like that. And then plug in the output of the splitter to the output pin, and one more output pin of a single bit, which is the overall carry of the entire thing. So this is this carry out of the entire 3x3 adder, 3-bit by 3-bit adder. And this one here is our carry in. So now we have a full 3-bit by 3-bit adder. And I got some questions in Discord, so let's check that out. All right. Nope, that's not new stuff. Okay. So do we have any questions now about this particular 3-bit by 3-bit adder? And if someone's complaining and say this one does not look anything like the text version of our example, all you have to do is to rotate your head 90 degrees counterclockwise to look at the logisim diagram. Then it will basically have the same layout as the text version. All right, Justin is typing. I'm gonna wait a little bit. CInOut is part of the binary number. Technically, no. So technically, when you have a 3-bit by 3-bit adder, the inputs are 3-bit wide, and so is the sum. It's also only 3-bit wide. But we do have the extra carry out as a different pin. So it is not part of the sum, but it is an extra output pin. So we'll talk about why there's an extra output pin. But you can also kind of imagine right now that I can stack these 3x3 adders instead of being a full adder, but they're also stackable. In other words, I can stack two 3x3 adder, feeding the output of the first, feeding the CInOut of the first one to the CIN of the second one. Then we have a 6x6 adder. Does it make sense? So as long as I keep CIN and CIout, I can make larger and larger adders just by stacking. Is that okay? Okay, I'm just gonna double check. Okay, all right, cool. All right, so now that we have a circuit like this, I'm not gonna build a tester, just for this yet, okay? But I can go through some, just kind of basic checking to make sure that this works, right? So right now it is already working because it is saying that if CIN is a 0, and we're adding 0 to 0, then we have a result of 0. So that works, right? So let's try 1 plus 3. Okay, 1, 1 is 3 in binary. And we end up with a 1, 0, 0, which is 4 in binary. So it does work. And now we want to see, okay, when is it gonna overflow? I shouldn't say overflow. When is it gonna have an overall carry of 1? Well, if x is as large as it can get, which is representing 7, and y is 1, then the sum is technically 8, which is 1, 0, 0, 0. But since the sum itself is only 3-bit wide, it can only represent the least significant 3 bits of the sum, and then we end up with an overall carry of 1. So once again, the reason why we do it this way is now we can stack 3x3-bit adders to become 6x6-bit. Then we can stack 6x6 into a 12x12 and so on. So it makes it kind of scalable. So do we have any questions about this particular adder? which is called a carry ripple adder. So let me name this circuit here. Okay, I'll just put a label into the circuit. Just kind of, this is just for commenting. This is also what we call a 3x3 carry ripple adder. All right. So now the question is, why do we call it carry ripple? Okay. Well, one thing you can see is there are interdependencies between the full adders, right? So let's track down those wires and figure out which one is telling us that there is a dependency. If you look at the wires going into X, they don't have any interdependency because the X of every single full adder goes to the input pin. In other words, as soon as the input pin X has a new value, all three all three full adders will start to work at exactly the same time. So they can simultaneously work. It's not a problem. The same thing applies to the Y bits, right? Because you can see all the Y pins, the Y input pins of the full adders, they all connect to Y as an input pin. So that means if Y changes, then all three full adders will basically change at the same time and try to compute the output at the same time. It's not a big deal. But when you look at the CInOut and the CIN, now we have a problem. Because when you look at the output of column 0, the carry output feeds into the second one, which basically means all three full adders will basically simultaneously work, but when the first full adder is done, it will update its own carry output, which means the full adder of the second of column 1 will now say, oh, hold on a second here, what I just computed is now invalidated because I just got an update of my own carry in. So the column 1 full adder will now go through the whole process again, update its own output. Now, if the carry output of column 1 changes, then the full adder corresponding to column 2 will now say, oh man, I just finished the computation. Now you tell me that the carry in is different. So now this particular full adder corresponding to column 2 will have to basically do all quote unquote do all the calculations again in order to update this particular bit of the sum and also this particular bit which corresponds to the overall carry of the entire adder. So what is the bottom line? The bottom line is the total amount of time to finish this computation is now proportional to the number of bits. Now, why is that? Why is there a delay from the input to the output? If we go to the lowest level, which is this design here, we can see that it has got 2 levels of gates, right? This is one level of gate. This is another level of gate. Each level of gate has a time delay. What do you mean by there's a time delay? Isn't things kind of simultaneous? The answer is we wish. We wish everything is simultaneous, but they are not. So what I'm going to do is I will go to the transistor circuit. Okay, let me just open it again. In my let's see here. I think I put it into the tester folder. There we go. Okay, I'm gonna pull this up to the screen over here. Remember this guy? I hope so. So now the question is, when you look at this, and if I make some changes, okay, if I just flip one of the inputs like this, and then flip the other one like this, you can see how the output is really changed simultaneously. But that's only because we cannot visually see the propagational delay. So what is happening here is, let me just do this one more time. Okay, when I flip one of the input pins from 0 to 1, Okay, if I flip this one, okay, you can see how this wire, just kind of lights up to light green, kind of like right away, and then this transistor, is just affected right away. Or if I just turn this one from 0 to 1, then everything seems to happen at exactly the same time. But that really is not the case at in real devices. So why is it not happening in real devices? Why is there a delay? So I'm going back to Zerno because I want to show you a picture, because this explains why there are propagational delays, and I think it's kind of important. So we'll just take a look at a gate. Whether it's an N-type or P-type doesn't really matter. Okay, so we're looking at an N-type here. Okay, and we want to look at just this portion over here. Okay, if you just look at that portion, doesn't it look a little bit like this particular symbol in a circuit? For those of you who have taken the class in circuit. Okay, this is a capacitor. So there is intrinsically a capacitor between the gate and the substrate of a MOSFET, of a metal oxide semiconductor. FET is field effect transistor. So there's inherently a capacitor here. Now, even worse than this, every single wire has inherently some kind of resistance. Okay, it can be very small, but it's still there. So that means there's actually some kind of a resistor here before it connects to some kind of input pin, which is all the way over here. So that means if originally the voltage over here is 0, and you say, I want to change it to a 1, it takes time in order to go through a resistor to charge up this capacitor so that this eventually will be the same voltage as the pin. So it takes time. That is fundamentally one of the reasons why there's a propagational delay, because each transistor inherently has a capacitor built into it, and every wire has intrinsically a resistor built into it. Now the real picture is even worse than this, because when you look at the real picture, there's also an inductor built into every single wire. So with an inductance, resistance, and capacitance, if on this end, if on the pin end, we're looking at something like this, which is a really nice square wave, on the other side, it's not going to look like that at all. Okay, it's going to look like this. Okay, so that means the change is not simultaneous. When you change the input pin from 0 to 1, it takes a little bit of time for the transistors to respond to the changes of the pin, and this is at the lowest level. So when we go back to the higher level, which is this particular design here, this means that there's a delay. If these wires change, there's a delay between these wires changing, and these wires changing the state. And then of the AND gate over here, there's a delay between the changes of its input wires and its output wire. And as a result, this entire design has a propagational delay. This is a half adder. It is utilized in a full adder. But when you look at a full adder, you can also see the interdependency between the half adders, because the output of the first half adder, this particular wire over here, which we know as Q, goes to the second half adder. So this means the propagational delay of a full adder is approximately twice of the propagational delay of a half adder. When you look at a 3x3 bit adder like this one, this full adder itself has a propagational delay, which means from the time its input pin, like these guys, changes to the time the carry output changes, there's a certain delay. So until that time, whatever the second full adder is outputting, it will output something. Okay, it's always outputting something, but it may not be valid. So as soon as this wire changes, then the second full adder now has to go through all the propagational delays again in order to update its own output. One of the outputs, which is, oops, okay, I just did something stupid over here. So one of its output, which is this Y over here, is going to the third full adder. So now, after the second full adder is all done, the third full adder will now potentially have to update its values again. So the more bits you're adding, the more full adders are connected in a chain, which also means the propagational delay to get a final result, which is the sum that we want, and also the overall carry that we want, that time will also lengthen. It is proportional to the number of bits. In other words, if you use this kind of a design, a 32-bit adder will take 4 times as much time as a 8-bit adder, and then a 64-bit adder will take twice as much time as a 32-bit adder. Is that okay? Does everybody understand why a carry ripple adder is kind of slow? It is proportional to the number of bits, the amount of time it takes. Okay, excellent. Okay, so this is really important because this is the reason why we do not use carry ripple adders in real life. Because if Intel decides and go like, well, this is really easy to implement and it's easy to look at, we'll just go ahead and do it this way. And if AMD can come up with a different type of adder that is a lot faster, then guess what? AMD is going to outsell, Intel. Well, that will never happen. But AMD will then, have a gain in the market share because people will say, hey, AMD processors are faster. All right? So let me just go slightly back to what I said, okay? AMD will never outsell Intel simply because AMD does not have enough fab capability to outsell Intel. So even if AMD says, we are owning the market, okay, all of our processors are half the price of the Intel processors and they're twice the performance of the Intel processors, they cannot overnight take over the market because they cannot produce enough processors to saturate the market at all, not even close to what Intel can do. So that's kind of interesting because nobody knows the actual size difference between the two manufacturers. Intel is much larger. It's kind of like saying, what if GM dies? Do you think Subaru or Honda can take over the automotive share that GM is leaving behind? The answer is no. The manufacturing capability of GM versus Honda or Subaru there's no comparison. There's just no way that the smaller manufacturers can take over the market. Not in a very short amount of time. It would take a long time to ramp it up. Okay, so now what are we going to do? This is not good. Okay, it takes way too long. So now we go back to the notes. Okay, let me see where did I put my notes? It's all the way down here. There we go. So the carry ripple design is really scalable. It's easy to understand, but it sucks because it is really slow. So we are now at a point where we are now in section 6. So let's go ahead and take a look at section 6. So the heading of section 6 is really misleading. But wait, there's more, which implies there's a little bit more. No, actually we got a lot more coming. I'm just looking at the time. We got about 14 minutes, okay, which I think is enough time to go over some of the concepts, but not all of the concepts. So what we see here, okay, so let me pinpoint what I'm referring to. So what we see here is the definition of ki plus 1. I mean, is that surprising anyone that we now define ki plus 1 to be the carry of xi, yi, and this plus over here means disjunction, it means or, the carry of qi, ki. It really should not be surprising because we have gone through just this equation several times just today. Okay, so that should not be surprising. Going from the first row to the second row, okay, is that really surprising? that we implement the carry function using logical AND. It looks like multiplication, but remember, this is my shorthand of conjunction, is to borrow the notation of multiplication. So that really should not be surprising either, right? Going from the second row to the third row, okay? The difference is qi becomes the result of xi, yi. Well, that really should not be surprising either, because that really is the definition of qi, okay? Qi is defined to be r of xi, yi, okay? So that's not surprising. And then we look at the r of xi, yi, and we expand it to xi and not yi, or not xi and yi. Well, that's not really too surprising either, because this is what we talked about yesterday. Okay, we can use it. We could have used exclusive or, but but since I don't want to introduce another Boolean operator into the whole thing, I just kind of use the longer version, but using only the Boolean operators that we are familiar with. Okay, so everything up to the fourth row should be like, okay, everything is just going by definition. From the fourth row to the fifth row, okay, from here to here, that is distribution, okay? Now, this is CISP310, so I will not require you guys to be able to do Boolean algebra. But if you're in my CISP440 class, then I will basically ask you guys to also know how to do Boolean algebra stuff. But that's just Boolean algebra, okay? It's distribution. And then from the fifth row to the sixth row, the difference is this is now this, okay? In other words, xi, yi, or xi and yi is the same thing as xi and yi and true. Okay, hold on a second here. Are we really sure about that? So, so when you see something like this and you go like, I'm not really sure that is true, you really should start to question it. But instead of just questioning it, you can also use a truth table to prove that really is the case. I'm just switching back to the Zerno screen here, because I want to show you why, how easy it is to prove something like that. So at the heart of the question is we are asking if x is a Boolean value, is that the same thing as x and true? Okay, that really is the question. So how do we answer this question? We use a truth table. In the truth table, x is an independent, is the only independent variable which has values of zeros and ones. And then x and true is the expression that we want to test. So when x is false, false and true is false. When x is true, true and true is also true. So right away, we can see how this column and this column are identical on every single row. So that means x equals to x and true is in fact a valid equation. So switching back to the class notes here, so that means when we look at xi and yi, and then later on we say, well, I want to call this xi and yi and true, it's perfectly okay. There's no problem with this approach. So are we good so far with this little bit of Boolean algebra? And once again, I'm just going to double check to make sure my Discord is still working. All right. So okay, so we got some confirmation. That's good. So now the next question is, can I start with true and then end up with true or something? Okay. Does it work? Okay. Intuitively, it should work right away, right? Because because if an expression is true to begin with, doing an or can never turn it to be false. But formally, can we prove it using a truth table? And the answer is, yeah, pretty easy to do this one too. Because what we do now is we say, this is x, this is true, and this is x or true, okay? Now, x is the only one that can potentially have different values, okay? It can have values of zeros and ones. True is just true, right? Because it's a constant. So we now look at x or true. X is 0, 0 or true is true. X is 1, true or true is also true. But this time we are comparing this column versus this column here. We can see how the values corresponding to that column are identical on every single row. So this is how we can prove and validate that we can now turn this true to true or something. Okay, and that something can be whatever you want. Okay, ki just turns out to be what I need, but you can use anything you want, anything that is Boolean. And then from here to here, I used distribution again, and then from here to here, I replicated one item. Let me see which one I did. I replicated this one here. So this particular term is now appearing twice. It appears once over here, and it appears once over here as well. So now we have another question, right? Okay, in a Boolean expression, in an overall OR Boolean expression, can I mention an item multiple times and not change the result? So what do? We use a truth table. So now we switch back to a truth table, and this time we are asking, is x really the same thing as x or x? X is an independent variable. It can be true or false. When x is false, false or false is false. When x is true, true or true is also true. Oh, okay. These two columns, in fact, have exactly the same values for every single row, so they are equivalent. So now we switch back to our derivation. So this is why I can just take one item and say, I want it appear here and also over here. It is not a problem. So from here, let me scroll down a little bit. So from that, I started to group items. In other words, I put parentheses around these two, and I put parentheses around these two. The reason why I can do this is because disjunction is associative, meaning that when you have multiple disjunctions in a row, in a chain, the ordering of which disjunction you do first does not matter. Just like addition in a regular algebra or multiplication in regular algebra. The reason why I do that is because I want to look at this and say, we're going to do the reverse of distribution, which we also call factoring, because we can see that each one has xi, ki in it. Okay, xi, ki, ki, and then this one also has xi, ki in it. So I factor out xi, ki, and then whatever is left, which is yi from the first one, and then not yi from the second one, I put it into a second thing. Okay, this is exactly the same thing that you normally can do in regular algebra, is factoring. Okay, and I do the same thing with this one over here. The common term between this conjunction and this conjunction over here is yi, ki, and the difference, which is xi and also not xi, they are separated out into its own sub-expression. That's basically just factoring. So now on this row here, we look at xi or not, we look at yi or not yi. That is just true. Okay, so now we say, well, does that make sense? Okay, can we prove this? And you probably know, you can probably guess the answer already, right? The answer is yes. So we try to prove that. So this time we're asking x or not x, okay, versus true. Okay, x can be false, x can be true. If x is false, false or true is true. If x is true, then we have true or false, which is also true. Oh, okay. So when we compare this column to this column, they are identical. So once again, we just use a truth table to validate, key axioms in Boolean algebra. So we already know that this one is not really useful. Okay, so I should say, okay, let's go back just to xiki over here, and let's just use yiki over here, and then using these two, I do another factor because ki is common between these two conjunctions. So ki is factored out, and the xi or yi is on its own. Okay, so this is just a really long derivation in Boolean algebra in order to get the ki plus 1 equation to a particular form. So what have we done here? We haven't really removed the linear relationship between ki plus 1 requiring ki, because we can see that ki, which is all the way over here, still depends on ki plus 1, excuse me. So ki plus 1 is still dependent on ki, so that dependency has not been removed. For the homework assignment for the lab for today, it is super important to read this really small but really important paragraph. So what we're going to do is we are having two definitions here. We are defining g of I to be xi, yi. We are defining p of I to be xi or yi. Okay, doesn't seem very significant, right? Because gi is really just a conjunction of xi, yi, and p of I is just the conjunction of xi, yi. So what is the big deal of doing this? Well, if we do that, we can see how, now we can just replace this term with g of I, and we can also replace this term here with p of I, because those are the definitions of g of I and p of I respectively. So now we can rewrite k of I plus 1 to be g of I or p of I and k of I. Okay, well, from the perspective of the nature of the equation, this is not really much better than before, because ki plus 1 is still dependent of ki, so we really haven't changed that at all. However, if we use this and we plug in different values for I, we will start to notice a pattern. Now, I do have to finish this this slide by so I might have to lengthen the lecture time a little bit because it's really important to do this part here. If you use a 0 in place of I, in other words, when I equals to 0, then we get k of 1 equals to g of 0 or p of 0 and k of 0. Okay, it's just a straight substitution, right? I equals to 0, so wherever I goes, we replace it with a 0, and wherever I plus 1 is, wherever I plus 1 appears, it becomes 1. Okay, so that's no big deal. What about the case when I equals to 1? When I equals to 1, we start with this. Okay, so when you look at this equation over here, it's like, okay, what is the big deal, right? Well, the big deal is we know what k of 1 is now. So we substitute what k of 1 is in place of k of 1, and then we expand the equation, so we end up with this. In other words, we now can express k2 without using k1 anymore. Is that okay? Because this is the huge deal. Okay, this is the big deal of doing it this way. Is so k of 2 can only depends on g and the p terms and not the k0 anymore. Is that okay? All right. Okay, so I'm going to push this one more step. Okay, what about when I equals to 2? When I equals to 2, then k3, because 3 is I plus 1, is g of 2 or p of 2 and k of 2. Big deal, okay? K of 3 is still depending on k2, but hold on a second here. We just figure out what k2 is. K2 is this stuff here. So instead of using K2, and I now expand K2 to be this kind of long mess over here. And I also want to do the distribution. So once I perform the distribution, then K3 now becomes this kind of long-ish, expression. But what is the big deal? The big deal is K3 now does not depend on K2 anymore. It only depends on the G terms, the P terms, and just K0. Okay? But it still depends on the G terms and the P terms. Well, the P and the G terms are pretty easy to deal with because by definition, G of I is X of I and Y of I, which means I can simultaneously compute G of 0, G of 1, G of 2, and so on. They can all occur at exactly the same time. P of I is the same way because P of 0 only depends on X of 0, Y of 0. P of 1 only depends on X of 1 and Y of 1, and so on. So I can use one single propagational delay and come up with all the P and all the G terms. Okay, it only takes me one propagational delay to get all of them. Once I have all the P and the G terms, okay, when you analyze this particular expression and also this expression here, even though the second expression is more complex, but when it comes to the amount of time to get it done using logic gates, they use exactly the same amount of time. Now, why is that? Let's pick out the most difficult one. It takes one propagational delay to come up with all the P terms. Okay, K0 is presented as an input, so it doesn't take time to compute it. So that means to get this conjunction done, it's going to take two propagational delay, one to get the P and the second one to get the conjunction. This is going to take about the same amount of time. This one is going to take less time because there's no conjunction. So the one that it will take the longest time is this one over here. By the time this one is done, the other two are done already. So now we have three outputs. So it's going to take the third propagational delay to OR these three terms. So K2 is only going to take three propagational delay to get done. So we look at K3 and we ask, well, how much time K3 is going to need? The most complex term, once we expand out everything, is that one, right? But we already know all the P terms can be computed in one single propagational delay. So the conjunction of all the P terms and K0 will take two propagational delay because it just takes one additional propagational delay for the conjunction. But this is the most complex term, so when this term is done, we also know that this term is going to be done, this term is going to be done, and this term is going to be done. So the third propagational delay is going to be used to perform the disjunction so that we can merge all four components of the disjunction into the result. Wait, hold on a second here. K2 only took also just three propagational delay, and K3 also only takes three propagational delay. The circuitry for K3 is going to look pretty messy, okay, compared to K2, and the circuitry of K2 is going to look pretty messy compared to K1, but the amount of time it takes is identical. It takes three propagational delay to get to K1, it takes three propagational delay to get to K2, it also takes three propagational delay to get to K3. In fact, if you have K64, okay, it's a huge mess. But guess what? It only takes three propagational delays. So this is the main difference between this method of computing the carry bits versus the carry ripple method. Because the carry ripple method means K2 depends on K1, K3 depends on K2, and so on in terms of the gate topology, the way the gates are connected. But when we use this method, which is called carry look ahead, then every single carry bits can be done at exactly the same time. Every single K bit will be done in three propagational delays. So once we have all the k bits done, the q bits are already done already. So when we combine the k and the q bits, we get the sum bits, right? And then we are done. So the whole thing can now be done in, I think, 4 or 5 propagational delays. I cannot exactly remember how many, but it's a constant. Okay, your 8-bit adder will take the same amount of time as a 32-bit adder. That 32-bit adder is going to take the same amount of time as a 64-bit adder. That is why we want to use the carry look ahead method to come up with the design for an adder. So I'm gonna save this one for next Monday because I think we really got enough stuff already for you guys to digest over the weekend. We do have a lab today. The lab today is called the key to today's lab is multi, M-U-L-T-I, or lowercase. I'll pin it in Discord. But I want you guys to finish reading this entire module and also to get started with the next module over the weekend, because on Monday we are going to move from here to the next module, which I think is binary subtraction, okay, which reused a lot of the reasoning and even the equations that we use in this particular module. So being able to digest this module entirely and understand all of the concepts thoroughly is really important before Monday. And as I said, I will talk about this on next Monday. And I am going to pin the passcode in Discord. It's just MULTI, multi. And it's now pinned like that. There we go. All right, so you have the lab for today, which is due tomorrow. I know tomorrow we don't have a scheduled synchronous session, but it's still due in about 24 hours. So try to get this done, okay, as soon as possible. And don't forget to put an entry into your daily log. And then I'm going to take a short break of 10 minutes, so I'll be back at about 10:40 to answer any questions about today's lab. All right. Without any additional questions, I am going to stop the synchronous session, and I'll be watching for traffic on Discord now.